are happy to have the pleasure welcoming Ariel Rubinstein to our seminar.
Thank you very much. I should say at the beginning, that's the first time that I'm presenting this paper, probably the last one, I don't know, it depends on your response. It's not a typical paper of mine, much more typical paper I gave a few years ago here, which was the main subject that I'm working in the last few years, namely economy with no prices and no rates. That's something which is completely different. Let's move on to the paper itself. First of all, I should say that it's a joint paper with Univ from the LSE. Here is the guy. I don't know if you see him. It's a bit gloomy. It's always a bit gloomy. So that's this picture from the LSE a few years ago. Now, let me start with sort of experiment. I hope you have not seen the paper. I distributed it a few months ago. I hope you did not look at it. Those, if somebody did look at the paper, please don't respond. I will present a question, and I would like very much that you will think about it for a minute or so. So here is the question. A very small proportion of the newborns in a certain country have a specific genetic trait. Two screening tests, called A and B, have been introduced for all newborns. It's important for all newborns to identify this trait. However, the tests are not precise. The study has found that, number one, 70% of the newborns who are found to be positive, according to test A, have the genetic trait, and of course, 30% do not. 20% of the newborns who are found to be positive, according to test B, have the genetic test, and again, of course, the rest do not. The study has also found that when a newborn has a genetic trait, a positive result in one test does not affect the likelihood of a positive result in the other. Likewise, when a newborn does not have a genetic trait, a positive result in one test does not affect the likelihood of a positive result in the other. Suppose that a newborn is found to be positive according to both tests. Now, the question to you, what is your estimate of the likelihood in percent that this newborn has the genetic trait? That's the question that was presented to many students around the world, and now it's presented to you. Please, before I continue, please don't tell me, don't be embarrassed. It's not supposed to embarrass you. So please be natural. Construct an estimation without this.
Okay, suppose we know what the
No, not suppose, just a number. Do you have a number?
I'm looking to me.
Somebody wants there to say a number?
I guess.
A number. If you're afraid to say it. Without no, just a number.
70%.
70%. Okay, that's a kosher answer. Next.
1.14.
1%. A number.
Yeah.
1%.
14%.
14%. Good. Next, some more answers. There is already a disagreement. That's already good. Here senior economists, and they disagree about a simple question like that. That's good already. But more.
Very small proportion is lost in the whole
Very small proportion of the reverse. Very small, you know, you want 1%. More than 72. 70, please. 70. Speak louder. 70. Okay. Next. Okay. There's a shy, fine, but that's enough because actually you gave me more than I expected. It's a very disagreement, and all of you are wrong, and so that's good. And then let's analyze what's going on. Now, notice several things about it. We said here a very small proportion. You asked me what is very small proportion. I think that for naturally it's very clear. Very small proportion is very small proportion. It's clear for me at least. It's clearer than to say 1%. But it doesn't matter. I mean, take 1%, 0.5%. It doesn't matter. It's important for the question that this is small proportion. So the structure of this question.
If small is 20%.
No, but 20% is not very small.
If it were 20%,
if it were, but you
then 70 would be correct. Okay, yes.
Statement. But 20 is not very small. Nobody think about it. It's very small. So what's important here, of course, are the very small. And again, think about it as 1% if you want to stick to some number. Now, the information here is given not in the standard way that as economists we are used to. Because usually we are used to talk about false positive, false negative. And here, the information is given in a very different way, which I would like to argue that it's not less natural in many cases.
This is the doctor's way of
namely, please now talk. Louder.
This is how doctors do.
Excellent. Okay, so here, that's like doctors speak. Namely, it's actually very natural. It's not like economists do, but really people often have this information. Namely, there is some test, and now we don't know there is no, the prior is very loose, but on the other hand, there is the two companies that produce the test, give you information, the newborn was just born, immediately you do the test, and then eventually you know whether it's the trait or not. It's a very severe trait. So eventually you know whether he has the trait or not. And you know that we have statistics for one company that tells you that 70% of the positive are sick, and for another company it tells you that 20% of the positive are sick. That's information that you have. I think it's a very natural structure of information, which is not the standard way that as economists we are describing this on this. This paragraph, of course, is supposed to be a conditional independence. We tried in the best way, we worked very hard about it, we changed it many times just to say the word conditional independent. But to say somehow, now if you ask me, this is completely redundant. And because nobody in the undergraduate students will not think about anything like but in conditional independence. But since we wanted to be safe to some referees, and so some criticism we included it. I'm not sure that it's actually now we are testing whether to take it out would actually be improve the results or not. But let's yeah. Okay, and now let's analyze it in the standard way. So the sort of model that I hope you will agree with me that fits to this situation is the following. You have conditional independent schematic tests, denoted 1 to k, in this case k equal 2. S is the base rate, namely it's the frequency of the trait in the population. 50, these are the numbers that I give you, namely these are the 50 of the individuals who tested positive according to test K, indeed have the test. We assume that Phi K is about S, namely that this indication, a positive indication, the fact that it's positive does not mean that actually it's less likely to have the trait. Pi k is the probability that the individual is found positive in the k tests as the trait. And now the standard way to analyze it is by assuming that what are pk and nk. Pk and nk are the probability of the positive result in test k for individual with or without the trait. So 1 minus pk is the false positive, is the false negative, and nk is the false positive. And now, notice the following, that the ratio between the relation between pk and nk to pk is given here. Why? Because pk, what is pk? Pk is spk divided by spk plus this, and 1 minus pk is this divided by pk plus this. So the ratio between pk and 1 minus pk is the ratio between this and this. Good? That's standard. So the ratio between pi k and 1 minus pk, pi k, it's a notation for not the best, but okay, the ratio between them is the following. It is the probability that all the k, in case that is yes, that all the k traits, tests would be positive, is S times pi pk. The probability is that if he does not have the trait, and still the k traits will be positive, is this. Right? So the ratio between this and this is the ratio between this and this. Clear? Now replace the pk divided by nk by 1 minus s times pk divided by 1 minus pks. And you get this. Okay, so that's the ratio between pi k. That's the correct, that's what we wanted to write. Now, in our particular case, the activation of this formula would lead to this, namely 7 times 1 minus s divided 12s. But just put it into this. Okay? Now notice several things. Number one, this of course depends on S. That of course depends on S. In particular, if S would be 20%, then you would get exactly 70%. Now you don't need this formula for this. Because what does it mean that S is 20%? S is 20% and the test B gives, being positive gives you 20%. This means the test B is completely, does not have any information. So you can just ignore it. Now think about it that you have only one test. And let's say that the accuracy of the test according to this definition is 70%. Then you know there is only one test, forget test B. There would be only one test. And this test you would get from the producer the information that 70% of the positive have the trait. He is positive. What's the probability that he has the trait? More than 70%. Again, let's repeat. Forget now of there is some S. Okay. There is only one test, and he's positive in the test. And you get information that 70% of the people who are positive in the test has the trait. What is the probability that this guy, assuming that he is positive in the test, has the trait? 70%. So actually, and that independent of the base rate. So that's one of the features of this structure, that if you only one test, you don't need the base rate. But if you have two tests, you need very much the base rate. You need very much the base rate. You can see it from the formula. But again, I would like to persuade you in this without the formula. As you say, if the base rate is 20%, then the test, the positive in B is you can ignore it. And then you have only one test, and then the outcome is of course 70%. Of course, if the base rate will be 70%, then it would be only 20. So of course you can see from that the base rate is crucial for the aggregation of the two signals, which is not true about units. Number two, look at this formula and see the following feature, which is probably a little bit unintuitive to some of us. That would be, take S to be very small. If S is very small, the ratio between pi and 1 minus pi go to infinity. Namely, the pi is going to 1. Namely, the correct answer, actually from the answer that were given, your answer was the only one which was qualitatively correct, because you said it's about 70. But actually, it's not just about 70. If S is very small, it's very, very high. Okay. So here are some of the features. Some of them I talked already about. So first of all, pi k depends on S. If k is very larger than 1, so this depends on S. If one of the tests is equal to, one of the feature equal to S, then you can ignore. That's what we said before. Additional positive result increases the probability the individual has the trait. Assume that the fit J, all the feet are above S. And if S converges to 0, if you keep all the other phi k constant, then the probability goes to 1. But the guy is the
Number 2 could be inequality, right? That's so equal. But only equal.
Here? No, only if S equal to phi j.
If the probability that the testings are positive is 20%, but 30% of the people have it.
So this is goes in the other direction. We cannot. Okay. So these are a feature. There is another feature which it's not so important, but there's an interesting feature of the non-convexity of information. Because if you have if you have k test and you ask yourself what is the marginal value of additional test, so this is the probability. So the marginal value of the test actually is not decreasing, but that's not very important for this. Okay. Now, what people do? Let's go back to your answers. One of you would say 14%, right? You multiply 20 by 70. One of you said 1% or 2%. Namely, I guess you know the information. You talked only about the basic. You said 70%. You took the maximum. You get an answer which is above 70. When we give many students to answer this question, we got many answers. We get always, but in such question we get more or less everything. But the more common formula, the more all the answers that had some clean logic were the following. This is the multiplication, that's a 14% in this case, just multiplying with this. This, may I say, it's quite a clear mistake. The max, not uncommon is the average. 70-20, what can you do with it? Taking the average, 45 in this case. There is a small amount of people who actually get the answer, which is 76%. And that's quite an interesting answer. And I have some indication that actually this answer was given by some more sophisticated students. This number is always above the max of phi1 and phi2. It's always, of course, above the max of phi1 and phi2. So qualitatively, it always gives an answer which is, in some sense, right. The logic of it is wrong. It's some sort of independence of something which is, of course, is not independent, and etc. But it's definitely something that we do observe. So these are the four formulas that we do observe, and we will talk about them again and again. Let's see the remarks and the end. Now, there is a phenomenon that was detected many years ago. It's connected with the Kahneman-Tversky and Maya Bar-Hillel and other already in the 70s, which is called the base rate neglect. Namely, the tendency of people to ignore the S, namely the base rate, which is, as you've seen here, which you should not ignore. The main fact that people use this formula does not mean there's a base rate neglect. The reason is that still it may be that for different S's, they would use different formula. For example, what you say, that if you would say that S is 20%, you would use the max. And if S would be, I would tell you 0.001%, probably you would use this. So the fact that people use it it's not exactly the same like base rate neglect, but notice, of course, that all the formula are based by themselves, ignore the base. Okay. Now, let me tell you a little bit about the experiments that we have done. So here we come to some methodological question about experiments. I could give you probably a full lecture about why I dislike the procedures that experimental economics are using. So I will not give it, but I will just hint to some of you. The first way, most of the experiments that I've done in my life, I've done on the basis of this website. This website I constructed about 20 years ago in order for pedagogical reasons, mainly to persuade students again is use less, not use full, use less. So the idea was that students of courses in Genfrey get some questions and they answer, and then I find it a rhetorical trick to tell them, look, you see your answers and you see the results of the standard analysis, and there is a big gap, and so Genfrey is not, you should take it with a grain of salt before you want to apply. And that's my approach in general about Genfrey. So that's the website. Now, this website was relatively succeeded more than expected, and now thousands of students who agreed to get more answers. And then from time to time, I send them questionnaires, and they respond. And these are now, some of the students are not students anymore, some of them are not so young anymore. But this is a quite interesting collection of people. They did study Genfrey at one point. They are from a variety of countries, including small countries like India and China. So it's not only California and Tel Aviv. And and this is done always without any payments, no monetary. Ideologically, I'm against paying people for experiments. So, which is of course a big sin for experimental economists. And it becomes a clash with experimental economists. I think that paying incentivize students is subject is nonsense. It's a waste of money. And it's a barrier to entry to the experimental economics, and nothing more. Of course, there are some people that think otherwise. And so initially, we ran these experiments on this website. But then we did the scene, and we did run it also. Because we have to admit absolutely that it's not because we think it's good to do it, but just because otherwise we don't have any chance that anybody will accept this paper to the most promoted journal. So we did run it also through University of East Anglia and NYU and some labs. So we did it in the procedures which were more or less kosher. Although actually still we did not pay them, by we don't incentivize them exactly, but we did run it in this procedure which is more kosher according to this protocols of experimental economics. I said already something like.
I'm sorry, maybe you don't want to go in that direction. So people that paid subjects, they have, I guess, the reason why they chose to do so. So you say that that doesn't work or that gives wrong incentives. What's the incentive for participants to take part in this experiment?
Well,
in comparison
what
to
nice about human beings is that many of them are ready to do things without any, just because of fun, because of interest and nothing more. And these are probably the people who take these experiments more seriously than students who are paid $4 to sit in some lab with them. That's number one. The question is, whether they, and let me demonstrate, explain something. I will look at we did pay, so there are two questions. Number one, why does students agree to participate? And here, one of the possibilities is just to say, you will get $7 if you participate, independently of what you do. So there is incentive, even if you're not interested in the questions to participate. But there's a second question, that's easy. The more difficult question is, what incentivizes the subject to answer a serious answer? What did the answer incentivize you to answer? And still you didn't think about it and you gave some answer.
But you insisted.
You
were very pushy. You kept looking at people. People felt embarrassed.
But still, only 4 people respond to it.
But yet there was a peer evaluation. If I give you a stupid answer, this reflects on me, and they all see me.
That's the reason not to
For
give
the
an answer.
students, it's the personal answer.
Yeah, but the people who didn't give the answer, 4 to 5 students, 4 or 5 faculty gave an answer, and they were very strong in it, right? Okay, in any case, the question is, the answer is in some sense empirical, namely you can do one way or another and compare the results, and I will show you something. But in any case, the question here is actually how to incentivize people to give the right belief. And the method that usually is used by experimental economists, traditional experimental economists, is by something of this kind. It's a method that actually, to my knowledge, the first to suggest Murphy Winkler already in the 70s. And the idea is to give a sort of a formula to pay you in a way that if at least you are expected utility or expected money maximizer, that you will give the right answer. Okay, that's the regular trick, quote unquote, that is used by experimental economists. Now, there are many formulas to do it and many ways to do it, but let me just demonstrate to you one experiment that I've done again in my methods. And notice that in this case, actually, it's not, okay, look at this question. This question is the following. I ask people, imagine that you are choosing a number between 0 and 100. You will be paid according to the formula 100 minus V minus choice squared divided by 100. The variable V gets the value 100 with probability 30% and 0 with probability 70%. What is your answer? That's the standard way. That's the standard way that experimental economists use. They do expect in this case that the derivative and whatever you do, and the right answer is third. And you're supposed to say the percent that you believe that is success. Now, in the experiments, usually it's not done, of course, to elicit what is clear. It's usually supposed to elicit a belief, which is subjective. But because people believe that the answer to this question will be 30, They believe that if I give them this incentive, monetary incentive, they will give me the right incentive. They the right, their subjective right, correct subjective. Now, this particular experiment just demonstrates that this method does not work even if you give the number. So in this case, you see the responses are about 500 students who answered. Only about 24% get the answer. If you test majority, give either 0 or 1, which is much more natural answer than. If you take the opposite, and the 70%, again, only 25% said 70, and again, 41% goes in the averages. So there is no any reason to believe that this method, the experimental economists are so proud about, and there are so many papers about this system, and this usualistic belief is as give any incentive to give anything which is close to this. Yes.
Why does it not incentivize these students?
Sorry?
There's no incentive. They're the same.
I'll show you that. I'll show you this. Okay, in any case, that's my methodological point at the moment. Why I don't incentivize students, a subject. I don't believe in this method of incentivizing in general, in particular in regarding beliefs. I don't believe that it has anything to do with eliciting beliefs. Okay, so let me now show you the results of the experiments. The experiments was a series, what I will report here is not all the experiments that we ran on my website, but it's only the experiments that we ran on the kosher, quote unquote, lab environment. So each question, the structure of the questions that we have just seen, and let me repeat. Always there was a background story about the characteristics that is present in the population, plus some statements like a very small proportion or even a number about the frequency of this characteristic in the population. Then there was information about 2 stringing tests in the same way that you've seen before, namely the probabilities, the percent of individuals who are positive, the characteristic, giving that positive in the test. Then there is some explanation, non-technical explanation of conditional independence, and then there is a question: what is your estimate of the likelihood that an individual is positive in the 2 tests as the characteristic? That's the structure of all the experiments that we ran. And so Q1 is the question that you've seen. Q2 was again with a very small proportion here, but in here instead of 70 and 20, there was 80 and 60. Check there. Q3, this is a question that instead of trades, the story was a bit different. Namely, a very small proportion of the undergraduate students who graduate from a certain university continue on to a graduate degree. The study has found that 70% of the undergraduate students who take course A continue to graduate studies, and 20% of the students who took course B continue. And then the question of what these students took courses A and B, what is the proportion? What is your belief that you will continue to a graduate degree? So we changed the story. So let's so with the Q4 and Q5, but let's first talk about Q1 to Q3. So here
Are the 2 stories supposed to be completely parallel? Like they're supposed to be parallel in terms of the median weight theory? The graduate versus the
yes.
Because the graduate one sounds kind of like cause and effect rather than right, take a course and graduate. Like as opposed to the testing scenario where clearly the trait is independent, they are irrespective of the test. This is what
So that taking the course A could affect, but why it makes a difference. But in any case, that's the story. Even if it's not exactly the parallel, it's quite parallel. Okay, so let's first see the results about these three questions. So again, Q1 is the question that I asked at the beginning. Q2 was the same as 87-60, and Q3 it was same again 70-20, but this time regarding the students. Now the results are not exactly, of course, the same for these questions, but I must say we don't detect anything significant different between these three questions. Namely, there is a heavy use of the three procedures that I talked about, namely the multiplication, the average, or the maximum. You see quite frequently. You see here what you see in parentheses. This is the MC. This is 1 minus. It's the 76% that I was talking about. So there are very few here, but there are. And these are the people that I would say that, like you, that are qualitatively correct. And they give a number which is strictly above 7. Of course, maybe with some of them just wrote the number, just without thinking. But still, we see about 20% all of them that do qualitatively give an answer which is not bad. There are other, and other are all over, and some of them we can explain, we do understand what exactly they have in mind, but it's very, that's not interesting. The point that I wanted to make again is that there is a quite consistent, heavy use of three procedures, these three procedures. And these are the results with the incentives in the sense, not the incentive to give the answer, but namely it was done in the kosher protocol of the experimental. Response time, by the way, which is my favorite measure to study seriousness of students, is quite similar here along the answers. Namely, often what's happening is that one of the that you could say, could expect, for example, the numbers here are very small, so there is no significance to think about response time. But I cannot say that people who answer the average, let's say, the response time is not significantly lower than those who give other answers. So basically, it was quite similar. So,
these are in seconds, right?
Yes.
So 2 minutes.
That the median response time was a little less than 2 minutes. It's not a lot, but it's not zero.
That's how long it took to consider. So,
coming to compare the lab with the pilot. Pilot, I mean, again, pilot, I don't consider it pilot, but just for the reference. Pilot, namely, it's with my website, and this is with the kosher lab. The results are basically the same. I don't see any significant difference. There is a little bit in my website, there is a little bit more MC than here for this particular question. And the response time is actually larger. It's 147 seconds on my website, unless it's 118 seconds in the lab. Namely, on my website, actually students spend half a minute more, which is a lot. And so if he goes in any direction, it goes to the opposite, then people without any incentive to participate were actually more serious, at least in terms of response time, than in the lab. Okay, so this is just supposed to say the differences between this method, at least, is not significant. Here is another question, Q4. Question Q4, what we did is that we wanted to see some sort of consistency. So the story was again the story of the newborns, but this time there were 4 tests, A, B, and C, D. And the information about AB was 70-20, the information about CB was 50-40. And we wanted to see, and we asked people 2 questions. Alice is found to be positive in A and B, and Bob was found positive in C and D, and we wanted them to answer both to estimate the percent for the 2 guys. And we wanted to see whether they use the same method of same formula. And about 60% were actually consistent. 60% were consistent, and again, you see if it all actually, but they were more serious than the unique question. And again, you see 30% are chosen the same in the two questions. Answer the average. 15% both pair questions did the multiplication, and the 13% the max. 2% both cases chose the MC, and so on. So you see, I think this is a sort of some test to see that whether the use of the formula was coincidence or whether it was more serious, but more systematic. Of course, this is just repetition of two tests, but
if you ask questions with one test only, you ask questions
I should say
scenarios with only one test, without aggregation.
I forgot to say. You see all the 5 questions that I showed you, every student answered only one of the 5.
Yes.
So randomly, students were assigned to one of the 5.
Yeah, that I understand. My question is whether you try to ask them about scenarios with only one test,
No.
without aggregation. But maybe the problem,
Maybe.
the bias would be on
Maybe.
not related to the aggregation.
Maybe. Absolutely correct. It's a good idea to do. Maybe in the pilot we did, but I don't know. We did so many questions in the pilot. I don't know. But it's a good question. I don't have anything to report. Question 5 is the question we and here we did say that about 20% of the new parents, that's also connected to your question. 20% of the new parents are, I get the base rate, the S, 20%. I was supposed to ignore the 20. So the right answer was 70. And now you can interpret it in both ways. The results are not good. And if they did not understand, they did not absolutely, the max is the right answer, 70. And only 17% gave the answer. And it's not clear it's because doing the right calculation, or it's because they followed again the max formula. So that's absolutely, these are quite alarming results, which may go in your direction for your question. Okay. Good?
Yeah, I'm saying significantly less people said average.
Yeah, but again, I would not take very seriously the difference between 9% and 15% here. The numbers here were around at the end here, but we have something like 70, 80 students in each treatment. So I wouldn't apply here anything. 3% is very small, and 15% is significant, but that's all. Okay, so these are the 5 questions. Conclusion here up to this point, people are not doing whatever, maybe they do also other mistakes, but definitely they don't aggregate this information in the right, correct way. They do apply some formula, many of them apply formula, and the standard formulas that they apply are the N, the average, and the max.
On average, they do give us a lower probability of the year compared to the other one.
The average,
49%.
no,
The mean is 49%.
yes, the mean, I mean the mean of the answers.
Yeah, and it was higher before, right?
70, 20, was 51. So,
The results depend on the knowledge of
but
students.
for the aggregated numbers, I will not repeat it, but I will not put any significant.
Does the answer depend on the knowledge of probability, foundations, based on the correlated sample?
These are students of, by the way, in the pilot, I don't know about the students who come to the lab in NYU and the UEA in East Anglia. Some of them do study mathematics or economics or statistics, but I guess that many of them are not. Actually, on my website, I do know that these are students at least a good entry, so at least they really did some sort of calculation of probabilities or more than that. That's the, and by the way, without this question, what happened here when I asked you so if you did the answers, I repeated informally with many of my colleagues around the world and some coffee conversation with people and very, very serious people. Almost everybody gave the wrong answer. So I don't think that's an outcome of non-knowledge of statistics or probability. It is just activating.
I think so. The relevant discipline here is medicine, because that's how doctors give the answer in terms of sensitivity and specificity.
I like your comment before, but I don't have any doubt that if I go to the doctors in Yechigo, it will not be different. Or it will be worse.
Why do you think so?
Because I think many people before me, many years before me, like actually Kahn investigated with some of his famous experiments and doctors in Stanford. And the answers were exactly like in.
But the doctors are the ones who have to act on these decisions, unlike us, who just give free answers. But they have to operate.
So, okay, but still, no, I'm saying it's not regarding this question, but regarding similar questions. Similar with faulty probabilistic reasoning is one exactly. So I personally recommend that. Okay. Let me say that I must give credit to one experiment that was done before us many years ago. Ariel is quite famous. She did not invent the basis fallacy, but this was kind of first his point. But she continued this, and many years ago, in 1980, she did a question which is somewhat related to our question, but it's not the same. Because actually, that question here, actually, she get the information regarding taxes and so on, but she get the question regarding she get actually the false positive, false negative information. So her question, two car companies operate in a given city, the blue and the green, 85% of the cars in the city are blue, and the remaining 15% are green. The car was involved in a hit and run accident. There were two witnesses to the accidents, both claimed that the errant car had been green. The court tested the witnesses' ability to distinguish between blue and green. It found that the first witness able to identify the correct color about 80%, and the other 20%, etc. And the other 70%. And the question is, what's the probability that what do you think are the chances that the errant car was green, given that both of them were saying green? Now, she reported her N was 29, she had 29 students, and she claimed that almost 3/4 of them did the average. We repeated on this question, we don't get anything close to that. But in any case, that's a side question, and I just wanted to give the credit to Ariel. Definitely, it is completely a side point of her paper, but she had this paper. She had this question, these results which are very different than the results of people. But the question is not the same, but there is some connection. Okay, now what can we do with that? Another 15 minutes. Right. So what can we do with that? So we are theoretician, Kelly and me, and what we wanted, why did we do it? We wanted to do it because we wanted to jump on economists. And we wanted to jump on economists and say personally, and both Michael and me, we dislike, now I talk about this. I dislike any use of Bayesian formula. Probably I think that almost no paper of mine was using Bayesian formula. something is absolutely has nothing to do with real life, is the Bayesian formula. Now, saying that, there are of course billions of papers which were using the Bayesian formula, and we wanted to take one of those papers and to compare the analysis, the standard analysis that is done with where people are doing correctly, activating correctly the Bayesian formula or the Bayesian reasoning with assumption that subjects, that the players, the agents in the model are activating one of the procedures that we did find in the experiment. So that's the structure of this paper. The experiments, we argue that people are using something which is not the Bayesian, but something like the max or the average. And now the question is, if players, again, are using the max and the average, what would with the results of the analysis will be very different than if they are using the Bayesian form. And of course, the answer is yes, in a very systematic way. So what we did is that we took one paper which is quite famous by Dagen and team, and let me repeat on what they did and what we do in context. So the model is a model of a panel. It's a panel of any referees deciding whether the defendant is guilty or not. The probability of him being guilty is S. I now repeat on their model. So S is the probability that he is guilty, 1 minus S that he is innocent. Each referee votes either yes or no. The defendant is found guilty only if there is a consensus to be yes. It's sort of a jury decision. The referees vote simultaneously. Prior to voting, each referee receives a private signal. We analyze like that it is private signal is a number in the interval 0, 1. You can think about it as some feeling, subjective feeling probability that the guy is guilty. And the signals are ID and condition independent. Now, the CDF of the conditionals are denoted by F and G, and the density by F and G, and of course the assumptions about them are basically the following. The small f, the density, so F is for if he is guilty. So F is guilty, so it goes from, so it's something like, no, I don't know. So the small f, the density is going up from 0 up, and the G, the density conditional that is innocent, is going from positive to 0. Okay? So f is going to, that's the standard assumptions that are made about the densities. Now, don't ignore this, this is just standard calculations of the relation between the assumptions about the densities and the distributions. Okay, so the intuitive assumptions here are quite intuitive. Again, the density of if you're innocent, if you're guilty, is going up, and if you're innocent, it's going from positive to 0. Okay. Now, each referee wishes to convict the guy if he believes that the probability of being guilty is above Z. That's our assumption. Based on number Z, and I assume about Z that it's about 1/2, and I assume about S that it's less than 1. Now, this is equivalent to the assumption that each referee is consistent with the phenomenon and utility, which give number 1, the utility 1, if the correct decision is made when the defendant is guilty, and the lambda greater than 1 if the correct decision is made regarding the defendant, and the cost of finding guilty and innocent guy is larger than making the mistake regarding guilty guy, and 0 if the innocent decision is made. So that's the standard assumptions. This will lead to this sort of behavior. What's important here is just the number 0. So you can forget this. So each referee wants to convict the guy if he believes that the probability that he is guilty is about Z. Z is fixed. And I assume that all the referees are the same. They assume that the same. Now, there are analysis, like all the analysis in this type of models, depends on the following idea. So what do I get as a referee? I get the signal, so I translate the signal, the T is the signal that I get against a number between 0 and 1. And now the assumption in this model is that what the guy does, he is voting according to condition, makes the calculation conditional that is pivotal. Right? That's the standard approach. If you ask me whether it makes sense, my answer would be no. But that's the standard way, and in this case, we took the standard way and we made just one change. So here we follow the standard game theoretical analysis that approach that what the guy do is that they do the calculation conditional without pivot. So now the other approach are going to be the following. The guys get a signal T, get a number, his personal belief. But we take as a second signal the event that he is pivotal. Okay. So and the events that he's pivotal as minus I, namely all the other guys beside him are voting yes. And that's what we call the C belief. And now, what is symmetric equilibrium? Symmetric equilibrium would be here a cutoff sigma star, such that for every I, there is C belief. For every I, if T is below T star, then C belief is below Z. And if T is above sigma star, his belief is above Z. Let me repeat again. So this is the belief, I believe, that given that everybody is following the other n-1 referees, following the cutting point sigma star, the cutting sigma star, then this is my belief that is given. For being equilibrium, sigma star to be equilibrium, what has to be the case? That if my signal is below sigma star, my belief would be below Z. And if my T is above sigma star, my belief should be above Z. Right? That's the sensible definition of equilibrium, and that's the equilibrium that they use and we follow. Now, for them, the mu ICT sigma star is done by the standard Bayesian reasoning. Okay, and let me now just quote them. So the standard Bayesian reasoning is this formula. If you want to look at it, if not, just believe me that it exists. And the analysis actually is quite nice. And notice here two things. Number one, again, the new IT sigma are going to, there are two factors here. Number one is given the T, this gives me some subjective probabilities. So give me some probabilities that the guy is guilty. And given sigma, so the event that we have in mind is that the other n-1 referees voted yes. Namely, all the n-1 referees got a T is going to private signal above sigma. Now, the RK sigma, this is the probability that given that if there are K other referees, that's the probability that given that all the other K referees are voting guilty, that's the probability that the guy is guilty. So from the point of view of the individual, from the referee, he's supposed, the way that we look at it is that he's going to aggregate two numbers. This number and the other number is the number given the T, the personal T that he got, what the probability that the defendant is guilty given the T. These are the two numbers, the two variables are condition independent, and again, what they did is they proved whatever they proved, and let me just repeat on the main messages of Dagan and Martin. What he said is that the equilibrium condition. By the way, there is another equilibrium, which is everybody actually always approved. But we're talking only about non-degenerate equilibrium. They talk only about non-degenerate. There is a non-degenerate equilibrium here always, and it maximizes the welfare in the standard, the way that naturally the welfare would be defined. And but what's interesting is the following: that the optimal the optimal cutoff point, which is equal actually to the equilibrium cutoff point here, is such that the cutoff point is converging to zero, and the probability of an innocent decision given the optimal cutoff point is going to zero. Namely, the decision is correct. So the main message of that paper is that this process or this mechanism that you have endless reasons, they get you need a consensus. Will hit if the number n is very high. If you follow this type of reasoning, then it goes that indeed it implies the correct answer, namely the innocent will be acquitted and will be found guilty. Okay, so the answer here is extremely positive, and that's one of the reasons that this paper is very famous, and there are many extensions and continuations. Now, what we did is the following. We just analyzed the center, and we did follow unwillingly, but we did follow because we wanted to be as close as far as possible to their model. We did follow the idea that people are aggregated two signals, one the T, and the second signal is the other n-1 referees voted in T. And they aggregated, but not in the Bayesian way, but they aggregated according to one of the procedures that we do find in the experiment. So, for example, the average gain. The average gain, people, if the sigma is the cutoff point, if the personal signal is T, my C belief is the average between PT is the probability that given T, the guy is guilty, with Ri-1 sigma, which is the probability given that n-1 other referees voted guilty, and the cutoff point that they were using is sigma, then this is the probability that the guy is guilty. So we take the average between the conditional, the pivotal, I am pivotal, with the probability that I myself conclude from the signal.
Why the cutoff is the same for all the
Because we analyze symmetric equilibrium. We didn't look at whether there are also non-symmetric equilibrium. Everything is symmetric, so all the referees are the same. Okay. The cutoff point again is symmetric. All the referees here are symmetric. Okay, so such a game. So that's a standard game. It's a standard game. So it's not a standard, but only in one way. In the way that the subject or the players evaluate the probability that the guy is guilty, which is the base for their decision whether to vote guilty or not. Equilibrium here, of course, it would be better such that this will be exactly Z. That's because of monotonicity properties of these functions. Then there is always a non-degenerate equilibrium, which is characterized by this formula. And now I'm sure that you are don't follow exactly. It's not very important, but let me just jump to the conclusion. Without a proof, the proofs are very boring, just calculations. I don't believe that I was involved in it, but I was involved in it. But let me just go to the main point. The main point here is the following. There is a unique equilibrium, non-degenerate equilibrium. This equilibrium is beta star is above sigma star, namely the cutting point of the average gain is higher than the one in the standard game theoretical approach. Now, what is more important, interesting, is that this in the cutting point of the referees would be converged not to zero, but it would converge to some number which is calculated by this formula.
Ariel, what is
And therefore, once again, and therefore, since this number is strictly positive, then the result is that the defendant will never, almost never, will find conflict. Namely, in the equilibrium of the average gain, we get the result that almost always, the guy is equilibrium.
just forgot what Z and lambda are.
Z is okay. Z is the probability. Z is the minimal probabilities that you want if if you believe is above Z, you want to
Lambda.
lambda is that's the level of the welfare. You know, there was one lambda, namely that's the probability, that's a phenomenon utility of voting correct, of making the right decision in case that he is not guilty. So forget of the welfare, it's not important. What is important here? The defendant is almost never conflicted. Namely, of course, in one case it's right, in one case it's wrong. So, but in any case, the system does not work. According to this analysis, whatever was working with the baseline, if people, all the players play using the average procedure, you get a very bad result. The max game is the procedure that we used, namely the new IT, the max between PT and this probability. And in this case, the equilibrium will be defined by, since this number is always about this number, then that's the equilibrium definition, condition will be this. And then you can get the following result that again, there is equilibrium and it's actually below the cutting point is below before. But what is especially interesting is this, as n increases, the probability of convicting the guilty defendant converges to 1. And that of convicting an innocent one converges to some probability. So actually with the max, you get a result which is very different than the results that you get with the average. With the average, everyone is acquitted. With the max, actually the guilty is found guilty always, its probability goes to 1. And there is some probability that also the innocent will be found guilty. In terms of welfare, actually, surprisingly, we get the same welfare as we got before. Why? I'm not sure we understand. Well, I guess if I'm running out of time, we can say that in the paper we will find also 2 other things. You will find we looked also at the mix between those and the average. The idea here is that some proportion of the referees use the baseline, some proportion, fixed proportion of the referees use the average, and we analyze this. In this case, it's not symmetric equilibrium because here actually there are 2 cutting points, one for the average and one for the baseline, one for the average. And here again, we could actually come to analyze there is equilibrium. In this case, actually, again, the probability of conviction converges to 0. So it's enough that there are small number, you don't need to everybody with the average. If most of the people are baseline, but there is a small but fixed proportion of people who are averaging, that's enough that the equilibrium will be a very bad equilibrium. There are some other stuff in the paper, I'm not sure that it's so interesting. So, maybe I'm sure that it's not. Let me just conclude. So again, the structure of this lecture was the following. Number 1, let me just repeat. Number 1, there was the basic experiments that I wanted to persuade you that the averaging, the aggregating information here is not such a trivial problem. The basic intuition that even we have, and it took me time myself to persuade myself that this is the result, are not so clear. Number 2, what is very important for me is to emphasize the structure of information that we put here is not the standard information structure that is described in most of the paper with this type of information. And I'm not sure that I understand why actually the literature just found one way and when there is another one, which is at least very plausible in many, to say the least, it's very plausible structure in many circumstances. Then we wanted to demonstrate that real people are using, of course, not using the basic formula, that's of course not, but very systematically they use certain or many of them, use certain procedures, in particular the average, the max, the multiplication, and so on. Some do, like you, understand that qualitatively it's above, it has to be above the max, and but this is not done. And then we wanted to demonstrate that if you replace the Bayesian reasoning in a standard model like the voting model that we have described, we immediately will get results which are extremely different than the standard results. Of course, instead of this model, we could take other models. We are not going to do it. This was enough. Not fun to analyze this type of, but you can see that it can be done quite easily. With results like that. That's what I have to say about it.
Thank you.